Okay, so dear students, welcome to the third lecture of probability and statistics. And we will continue today with so-called random variable. So I recall what we did last two lectures and make a connection with today's lecture. So last two lectures, we considered the set capital omega with elements small omega, where the small omegas were called elementary events, and these elementary events were results of a random trial. The subset which we denoted as capital A, capital B, capital C, and so on, were called events. And we calculated probabilities of these events while we denoted these probabilities by capital P, A, capital E, B, and so on. From now, from today till the end of the semester, we will consider the following. We will consider so-called random variables, and these random variables are based on the fact that these elementary events are given a real number. So from a mathematical point of view, we consider a mapping X from the set capital omega, from the set of all elementary events, to real numbers. And what does it mean? It means that, in fact, these subsets must be also given some numbers, some numerical expression. But when these elementary events have some numbers, and they are given some real numbers, then it means that these subsets need a set of numbers. So therefore, from mathematical point of view, this random variable is a mapping not only from the set of all elementary events to real numbers, but it is mapping from a couple, all elementary events, together with its sigma algebra. So it means with the system of its subsets, to the couple real numbers and so-called Borel sets. I don't know whether you have experience with Borel sets or not. It is a special part of mathematical theory, and we don't need all details. Everything what we need is that, in fact, in these Borel sets, there are all intervals, open intervals, closed intervals, all points, and all unions of these intervals, which you can imagine. So there's nothing special on it. And the idea is that the events must be given some interval, some set of real numbers. Yeah? So that's the idea. But we can imagine the random variable as the mapping, or we can also imagine it as a random number. So, what does it mean? Some example. I use my favorite example with a die. So, we throw a die, so it means that capital omega consists of elementary events omega 1, one spot on the die, omega 2, two spots on the die, and so on, till omega 6. There are 6 spots. On the die. Yeah? And in this case, X, the mapping, can be naturally the mapping which gives to omega y, or omega I, I'm sorry, the number I for all 6 possibilities. So in fact, it means that even that there is one spot on the die is given the value 1, and so on, till the last situation that omega 6, there are 6 spots on the die, is given the number 6. So in fact, it means that this random variable X is nothing than the number of spots on the die. Yeah? So it is in fact a random number which describes how many spots are on the die when we throw the die. Then we can imagine the events, for example, as last time. So the event A is the event the number of spots is less or equal to 2. The event B, the number of spots on the die is odd, and so on. Then, instead of these probabilities, probability of A, probability of B, we can write in fact, so for the event A, we can write that it is in fact the probability of such elementary events whose image is less or equal to 2. Yeah? And just for simplicity, we can omit these omegas. So we can write just briefly probability that X is less or equal to 2. Yeah? And in fact, the event is the same. we said that the number the event is the event that the number of spots is less or equal to 2. Here we say the same. Probability that the number of spots is less or equal to 2. So the only difference is in notation. First we use only the even in the brackets, and now we have the behavior of the random number in the brackets. And so x is only the random number, and in order we have an even in the brackets, we need to describe some behavior of this random number. For the event b, we want to calculate the probability of such elementary events whose image belongs to the set 1, 3, or 5. And again, we can write just briefly that it is the probability that the number of spots belongs to the set of 3 numbers 1, 3, or 5. That's it. Yeah? So do not forget to write a behavior of random numbers when you work with random variable. It means with a random number. Don't forget to write the behavior of this random number, which gives us, in fact, the event. And so yeah, thank you that you solved the situation with the YouTube. Okay, and I will continue with the next slides. So the first, what we need to identify is notation and mention some properties. So the notation of random variable is usually given by capital letters, starts with x. Yeah, so x, when we have more random variables, then we continue with y, with z, and there's the notation which I will use in this presentation. Of course, it's up to you which notation you will use. So if you want to use a heart, a pig, or some sun, some picture, it's up to you. But in this lecture, I will use these capital letters x, y, z, and so on for random numbers. And then I will describe the behavior. So for example, x is less or equal to 2, x belongs to a set, and so on. And the concrete values, the concrete real numbers, will be denoted by small letters. Yeah, so there is a difference between capital letter and small letter. The small letter is used for concrete values, and capital letters are used for the random variable, for the random numbers. And as I mentioned, I will omit this omega because this notation is shorter, and I think that for you, for your imagination, it is much clearer. Okay, the properties. We will talk about many properties. So just for the beginning, let's mention that a random number is nothing, it's not science fiction. It is mapping from a mathematical point of view, but as I said, it is a random number, and random number is also a number. It has only random values, but it is a number, so we can do everything, all operations which we do with the classical numbers, we can do with these random numbers. So it means that the sum of 2 or more random variables is a random variable. The product is a random variable, and also minimum, maximum, and the random number powered by something is also the random number. It's also random variables. So don't be afraid of these random variables at all. And now I will mention very important term And this term will be used every lecture till the end of semester. This term is so-called distribution function. So I will give a special attention to this term. So the distribution function, which is also called cumulative distribution function, and sometimes it is denoted as CDF, is the function of a random variable x, which describes how is the probability cumulated till each value from R. So it is a function of a real variable u describing how much probability is cumulated till the value u. And this is the description which you must know, because it is the base of the rest of this lecture. How can we imagine this distribution function for, let's say, our random variable x describing the number of spots on the die, again in the situation where our random trials are throwing the die. So, when we throw the die, there can be one of 6 possible results. There is 1 spot, 2 spots, and so on. And we ask, what is the probability that the number of spots is less or equal to the value? So, what is the probability that the number of spots is less or equal to a negative number? The number of spots cannot be negative. So the probability is equal to 0. What is the probability that the number of spots is less or equal to 1/2? It is 0, because the number of spots cannot be less or equal to 1/2. So in fact, we will continue till the value 1. And now, what is the probability that the number of spots is less or equal to 1? There is one possibility which satisfies this condition. Less or equal to 1 can be 1 spot. And the probability that there is 1 spot on the die is 1/6. So, in the value 1, there is a skip in the function, and we continue. What is the probability that the number of spots is less or equal to 1.5? There is one possibility satisfying this condition, and it is again 1 spot. Because 1 is less or equal to 1.5. So the probability that the number of spots is less or equal to 1.5 is 1/6. It is the probability of one spot on the die. So this function is equal to 1/6 till the value 2. And now, what happens in the value 2? What is the probability that the number of spots is less or equal to 2? There are two possibilities satisfying this condition, 1 spot and 2 spots. So it means that the probability that the number of spots is less or equal to 2 is 2/6, or 1/3. And again, the probability that the number of spots is less or equal to, let's say, 2.7 is still, 2/6. It's still 2/6 because the elementary events satisfying the condition that their image is less or equal to 2.7 is 1 spot or 2 spots. And in this way, we continue further. And now, what is the probability that the number of spots is less or equal to 6? All numbers of spots are less or equal to 6. So now, the probability that the number of spots is less or equal to 6 is equal to 1. And what is the probability that the number of spots is less or equal to 10? All numbers of spots are less or equal to 10. And all numbers of spots are less or equal to an arbitrary number, which are greater than 6. So the function is constant, and it is equal to 1, because all images, all these numbers of spots are less or equal to a number which is greater than 6. And this is our distribution function for the number of spots on the die, for the random variable describing the number of spots on the die. Okay. Let's consider another example. Let's denote consider a game. And in this game, the success is when there are 6 spots on the die. Yeah? So it is the game with throwing the die, and we define success to be six spots on the die. And failure is the rest. So it means another number of spots. On the die. Then denote we have x there, so denote y, a random variable, a random number describing the number of successes in one trial. So what does it mean? In one trial, we can have either success or failure. So we can have either 1 success or 0 successes, nothing else. And when we consider our elementary events, it means that when we have one spot on the die, when we have two spots on the die, and so on, till when we have 5 spots on the die, the number of successes is 0. And when there are 6 spots on the die, it is our success. So the number of successes in one trial is 1. Yeah? So in fact, it is a random number denoting success by 1 and failure by 0. 1 or 0, success or failure. The number of successes in one trial. Everything is the same. What does it mean? It means that the probability that the number of successes is 0, so in fact the probability of failure is equal to the total probability of these 5 events. So because it means that the result of the trial is in the set omega 1 or omega 2 or omega 3 and so on till omega 5. So it means that the probability of failure is 5/6, while the probability of success is the probability of 6 spots on the die. So it is 1/6. Yeah? So this is the random variable describing the number of successes in one trial or describing success or failure. The distribution function of this random variable is the following. The probability that the number of successes is less or equal to a negative number is 0. The probability that the number of successes in one trial is less or equal to 0 corresponds to the situation that the number of successes is equal to 0. And the number of successes is equal to 0 with probability 5/6. So in the value 0, there is a skip of the function to the value 5/6. And then again, what is the probability that the number of spots, that the number of successes is less or equal to 0.54? Not important, arbitrary number between 0 and 1. The probability that the number of successes is less or equal to such number corresponds to the situation that the number of successes is equal to 0 and the number of successes is equal to 0 with probability 5/6. Yeah? So the distribution function is constant till the value 1. And what is the probability that the number of successes is less or equal to 1? All numbers of successes in one trial are less or equal to 1 because they are either 0 or 1. So the probability that the number is less or equal to 1 is equal to 1. And what is the probability that the number of successes is less or equal to 2, to 4, to 7, to an arbitrary number greater than 1? It is still 1. Because the number of successes is either 0 or 1. Yeah? So this is the distribution for the random variable y, describing success or failure in one trial. So in fact, you can see that for these random variables, the cumulative distribution function, and now I would mention the word cumulative, means how is the probability cumulated in the taken values. And the probability is cumulated in the way that in each value which is taken by the random variable, in each value we have a skip of the function, and the skip corresponds to the probability of the taken value. So when we consider the number of spots on the die, the values which are taken are 1, 2, 3, 4, 5, 6, and the probability of each value is 1/6. So we have 6 skips of the height 1/6, and in this way we skip to 1, or we jump to 1 in the value 6, and then we continue constantly till the infinity because there are no other values. In the second situation, it is the same. The probability of the value 0 is 5/6. So the first skip of the function is in the value 0, and it is 5/6. The second skip occurs in the value 1, and the skip corresponds to the probability of one success, to the value 1/6. Yeah? So there is the second skip. And there are no other skips because we have only 2 values which can be taken. That's it. But not all functions, all distribution functions have skips. We can consider something completely different. So the third example. Random variable z denotes the time of waiting for a bus. And suppose that the time between two arrivals is 10 minutes, and we don't know the time shuttle. Then, when we don't know the time shuttle, it means that we come randomly to the bus stop, and then the time of waiting is, in some sense, I will talk about this term later, but you can imagine something under this term. The time is uniformly distributed between 0 and 10 minutes. And because we cannot wait less than 0 minutes, we cannot wait for some negative time. It's impossible, it's nonsense. But we cannot wait more than 10 minutes. Because we know that each 10 minutes a bus will come. So 10, the distribution function is the following. As I said, the time of waiting cannot be negative. So it means that the probability that time of waiting is less or equal to a negative number is equal to 0. The probability that the time of waiting is less or equal to 10 minutes is equal to 1, because we can wait something between 0 and 10 minutes, but not more. So all times of waiting are less or equal to 10 minutes, and all times of waiting are less or equal to an arbitrary number greater than 10. Yeah? Of course, when we consider the time of waiting in minutes. Okay, what happens between 0 and 10? We cannot say that we take only some concrete, some finite numbers of values. We can take an arbitrary value between 0 and 10. So in fact, in each real number between 0 and 10, we have a small skip. So it means, in mathematical terminology, that the function is continuous. Yeah? So in fact, you can imagine this, this line segment as the set of many skips. Yeah? But in fact, this line consists of uncountable infinite number of skips is continuous. That's it. Yeah? So it is also the possibility, how can the cumulative distribution function look like? So this is distribution function, and we will work with this distribution function, as I said, till the end of the semester. So you will used to it. Here is at the beginning the instruction how you can imagine it in some special cases. What are the properties of this distribution function? There are some properties which are quite natural. So, for example, the last property, the property number 3, is quite natural because the distribution function is defined as a probability of something. Then it means that the distribution function must be in the boundaries between 0 and 1. So it cannot be negative, it cannot be greater than 1, it must be between 0 and 1. And what is the probability that an arbitrary number is less or equal to minus infinity? It is 0. So in minus infinity, the function must be equal to 0, or its limit must be equal to 0, because we will have some situations where the random number is not bounded. You will see later. And an analogous situation is in plus infinity. What is the probability that a random number, denoting whatever you want, is less or equal to plus infinity? All numbers are less or equal to plus infinity. So the limit of this distribution function in plus infinity is equal to 1. And of course, this distribution function is non-decreasing. It makes sense because when we consider our random numbers, there are numbers somewhere between minus infinity and plus infinity, and some of them are less or equal to a. When we consider, with some probability, they are less or equal to a. And when we ask for the probability that they are less or equal to b, what does it mean? All events, or elementary events, satisfying that the corresponding random number is less or equal to a are here. So they are the same for the random number being less or equal to a and b. And numbers which are less or equal to b, but not less or equal to a, are given somewhere here, and they cannot have negative probability. And so the probability of all these events together cannot be decreasing. It can be constant, as you could see, for example, in this case, but it cannot be decreasing. The probability cannot decrease. And the probability too is not important for our purposes. The probability is that the function is right continuous, but it is right continuous because we defined it as less or equal. You can find in some literature the definition that instead of less or equal, there is only less, and then the function is left continuous. As I said, it is not important for our purposes. I just wanted to show you where does it follow from, but we won't work with this property anymore. So a non-decreasing function lying between 0 and 1 is the distribution function, and its meaning is, I will repeat it many, many times, its meaning is how much probability is cumulated till the value u for all real numbers u. Okay. So, we will work with two types of random variables, but of course in practice their combinations also exist. First, I will describe these two types, and then I will mention their combination. Let's go back to our example. X, the number of spots on the die. It is the typical example of a discrete random variable because we care about the number. So the number of elementary events of the results of the random trial is finite. It can be also infinite, but it must be countable in infinity. What does it mean? It means that each elementary event can be given a positive probability, and the sum of all probabilities can be equal to 1. It is possible in natural numbers, in rational numbers. In these numbers, which are so-called countable finite. And when we can give a concrete probability, a positive probability to each of these elementary events, then we can work with the random variable as follows. The distribution function and it has the skips in taken value, where the skips correspond to the probability of the taken value. Then, when we want to calculate the probability that this random number is less or equal to something or greater to something and so on, it is, let's say, more natural or more useful to use the concrete probabilities. And so, for example, the probability that the number of spots is less or equal to 2 is in fact the distribution function in the value 2. But this distribution function is the sum of this skip and this skip. And these skips correspond to the probabilities of one spot and of 2 spots on the die. Yeah, so instead of this distribution function, we use the sum of the probabilities of the events forming this event. So in fact, this is the distribution function, but it is more natural to use these descriptions for the probabilities, because in our models, we described the probabilities that the random number take the concrete values. Yeah, so therefore, in this discrete case, we calculate with these probabilities more than with distribution function. And what else? We can use the relation which is written on the slide below. So the probability that a number is greater than something and less or equal to something else, it can be, oh, I wouldn't mention it in this case. As I said, it's not important for discrete variables, so I will comment this this relation later when I will talk about continuous random variables. Yeah, so I recall what is important for discrete random variables. There must be finite or countably infinite numbers of elementary events which can happen. Each of these elementary events can be given a positive probability, and then the distribution function is pairwise constant. It has skips in the taken values. The skips correspond to the probabilities of the taken values. And when we want to calculate the probability of some more general event, it is calculated as the sum of the probabilities of taken values. Another situation is in the second type of random variables. They are called absolutely continuous or sometimes only continuous random variables. And these random variables concern the situations when the random when the elementary events form some uncountable infinite set. So it means that we have uncountably infinite number of possibilities which can happen, and it occurs, for example, in the situation where the random number is time. Yeah? Time is continuous. So when we model, when we calculate the probability of time being greater than something shorter or something longer from something, then we have uncountably infinite, we have continuous numbers of possibilities. And in this case, we cannot define the concrete probability, the probability of concrete elementary events, because it's impossible to make a sum of uncountably infinite numbers of situations. So in these situations, which are, for example, time or heights, weights, or I don't know, temperature, or other continuous situations, we use a function f, which is called probability density. The probability density is a function describing where is the probability distributed among the taken values. So, for example, in the case when the random number is time of waiting for a bus, we know that the values which can be taken lie between 0 and 10. And they cannot be negative, and they cannot be greater than 10. So all of these numbers are between 0 and 10, and they are distributed between 0 and 10 uniformly. When we have some more general situation, so for example, an easy example, we have U there, so I will choose another letter. Let's say we time of waiting for a bus from the previous example when we know the time schedule. Then it means that again, the time of waiting cannot be negative, and it cannot be greater than 10. But because we suppose that we know the time schedule, so we are supposed to come to the bus approximately in the time when it should arrive. The probability that we wait something around 1 minute, some small number of minutes, is larger then the probability that we are waiting a longer time. Or maybe more general, I must admit what can happen to me very often, that I'm going to the bus stop, but since I'm always late, I'll come too late. So the bus is leaving and I must wait for the next bus around 10 minutes. But the probability is not the same for small values and for the values somewhere in the middle of the interval. As I said, this density is an analogy of the probability given to the concrete elementary events. So again, it must have some properties of the probability. And the property is that the probability of the random number being between A and B is equal to this area. And the area is nothing than the integral of this function from A and B. So the probability that the random number, sorry, not x, but z or v, it doesn't look nice. The probability that z lie between A and B is equal to the area below the function. So it means to the integral from A to B x. The same holds, of course, for v. Here, so it is the same for all continuous random variables. And it means that what is the probability that the time of waiting is between 0 and 10 minutes? It is equal to 1. So the probability, in fact, that the time of waiting is between minus infinity to plus infinity is equal to 1. We must be waiting for some time. So the basic property of this function, of this probability density, is that the integral from minus infinity to plus infinity is equal to 1. And here is the analogy with the probability given to the elementary events. This is the total probability, in fact, the probability of all elementary events. Okay. What holds? What does hold for the distribution function? When we have the distribution function, so I will continue. For example, here it is, of course, the same for z, for v, for an arbitrary continuous function. The distribution function is the probability that the random variable x or z, or in this case v, is less or equal to u. So it is the probability that V is greater than minus infinity and less or equal to U. But the probability that the random variable lies between A and B is the integral from minus infinity to upper boundary, to U in our case, from the density. So it means, in fact, that the distribution function is the amount of probability, amount of the area accumulated to U. And so it means that when I take U here, the distribution function is given by the area below the function from minus infinity till U. When U is shifted, it is the area to this new U. And so in fact, a distribution function denotes the increases of this area. So how does it look like in the cases of the random variable V? The probability that V, the time of waiting for a bus, is less or equal to a negative number is equal to 0. The probability that the time of waiting is less or equal to 10 or something greater than 10 is equal to 1. And between 0 and 10, it happens that first the probability increase very fast, because we have quite a large amount of probability at the beginning. So the increase is quite large. Then there are only small increases in the middle of the interval. So increasing is quite small. And again, there are quite large increases here in the end. So again, the increase is very fast. And there's the corresponding distribution function, meaning that we have quite high probability at the beginning, because it is cumulated very fast. Then we have less probability in the middle. Then we have again fight accumulation of the probability. So this is the meaning of the probability density. It is the function describing where is the probability distributed in the interval where we take the values. And okay, generalization. So before I will talk about the combination, I would repeat that I mentioned the definition of distribution function, which is the definition of a distribution function of an arbitrary random variable x, given by the description that it is the probability that the considered random number is less or equal to value u for all u's from real numbers. And we considered two types of random variables, discrete random variables, where the distribution function was pairwise constant, so it has skips, and the continuous random variables which have continuous distribution function, and it means that there are no skips in the function, so there are no concrete values which are taken, but the values are taken from some interval. So therefore, the elementary events cannot be given concrete probabilities, but we describe the taken values by this density function. And the last remark. In practice, we have random variables which can be combined from the discrete and continuous random variables. For example, let's call it W. The amount of rain per day, so it means participation during the day. Why is it a combination? Because when we have the case when there is no rain, then the probability of the value 0 is positive. So let's suppose that, I don't know, 40% of days are without rain. So it means that it is impossible to have a negative number, a negative amount of rain, negative participation. So the distribution function is equal to 0 for negative numbers. But then the probability that the amount is less or equal to 0 is 0.4. It is the probability of no rain. But then the amount is again continuous. So again, it is continuously increasing till the value 1. So, in fact, it is neither discrete nor continuous, it is the combination. But it is just a remark, because in this lecture, in this course, we will work either with discrete or with the continuous random variables, and we won't use this combination. It is just for your information that these random variables exist. And the second remark, so in fact we have remarks. The second remark for all random variables, I will again denote them as x. It holds that the probability that A is less or equal to x is less or and it is less or equal to b can be calculated as the distribution function in B minus the distribution function of A. Why? Because, as I said, when we want to calculate the probability that our value is somewhere between A and B, it can be calculated as the probability of all events which gives us the values less or equal to B. And we must subtract the probabilities of events which gives us the values less or equal to A. Yeah? And from the definition, it is exactly the difference between the distribution function in B minus the distribution function in A. Okay, it's satisfied for all random variables x, and moreover, for continuous random variables, it holds that this probability is equal to the probability where instead of less we have less or equal to A here, it is equal to the probability that instead of equality or less or equal here we have only equal here, and we don't have to have the equality neither in the first inequality nor in the second one. Why? Because the probability that the random random variable is between A and B is the integral. It means the area below the function from A to B. And what is the area of the line segment? The area of line segment is equal to 0. So it means that it is not important whether this point is included or not. The same holds for B. It is not important whether the point is included or not. And in fact, it means that the probability of each concrete value is equal to 0. Because the probability that x is equal to a concrete value, let's say c, is probability that x is no, it's impossible to write it formally in such a short time. So just imagine, what does it mean? It means that it is the area below 1 point in the density and the area of the line segment, which is the area below the function in 1 point, is equal to 1. Yeah? So the probability of x being equal to a concrete value is equal to 0 for all c. And despite the fact the area over the whole curve is equal to 1, we can talk about it on the exercise if you want. And from this, I can show you another term. As you can see in the first property of the density f, or before it was in the property, no. So it is in the first property of the density. There is written AS in the end. And this AS means almost surely, where almost surely means with probability 1. Why do we use the word almost? Because there can exist some events which doesn't satisfy this condition, and despite this fact, the probability of the remaining events are equal to 1. For example, the probability that the time of waiting so I just recall that to be time of waiting for bus. Then we want to calculate the probability that the time of waiting for a bus is not equal to, let's say, 3 minutes. It is 1 minus the probability of complementary event. The complementary event is that the time of waiting is exactly 3 minutes. But this probability is equal to 0. So the probability that the time of waiting is not equal to 3 minutes is equal to 1. The probability that the time of waiting is different from exactly 3 minutes is equal to 1. But despite this fact, there exists one elementary event satisfying that z is equal to 3. Yeah, it is the elementary event, meaning that the time of waiting is exactly 3 minutes. It can happen, but the probability is equal to 0. So the probability of the remaining events is equal to 1. And then we say that the time of waiting is different from 3 minutes almost surely. It happens with probability 1, but not all elementary events are included. Yeah, so this is a specialty in the case of continuous random variables, and if you have some questions or comments, we can solve it on exercise. So I would stop here for today. Thank you for your attention, and see you in approximately half an hour on exercises.